Very pleasant morning to one and all present here. I, Aditya Pal, feel an immense pleasure to welcome you all once again on the fourth day of this 5-day national level FDP on earthquake safe design and construction practices by AICTE Training and Learning Platform, brought to you by the Applied Mechanics Department, LD College of Engineering, Ahmedabad. I'm pretty much sure that all of the attendees would have thoroughly enjoyed the sessions delivered so far by our revered experts and eminent speakers in the field of earthquake engineering. And today also, we are quite privileged to have one of the eminent speakers who is joining us all the way from Canada, Dr. Svetlana Brzev, ma'am. Thank you so much, ma'am, for accepting our invitation. Now, I would like to introduce with the attendees the speaker for today. Dr. Svetlana Brzev, ma'am, has over 30 years of international academic and consulting experience related to the seismic analysis design and rehabilitation of reinforced concrete and masonry buildings. Ma'am also holds a bachelor's and master's degree in civil and structural engineering from the Department of Civil Engineering in the University of Belgrade, Serbia, and PhD in the earthquake engineering from the Department of Earthquake Engineering in the University of Roorkee, India. Ma'am is currently an adjunct professor at the University of British Columbia, Vancouver, Canada, and was previously a faculty at British Columbia Institute of Technology, Canada. Ma'am served as an international seismic engineering consultant for rehabilitation after the 1993 Latur, India earthquake, and is currently working as an international earthquake engineering expert on a few World Bank sponsored projects related to the seismic retrofitting of school buildings in Central Asia. Dr. Brzev is currently a member of the Board of Directors of International Association of Earthquake Engineering. Ma'am has published more than 100 papers and has also co-authored 3 textbooks related to the design of masonry and reinforced concrete structures. In 2015, she was named a Fellow of Engineers Canada for her contribution to the engineering profession in Canada. The introduction goes on for long, but I would like to cut it short because we are all eager to listen from the ma'am herself. So without any further ado, I would like to invite Dr. Svetlana Brzev, ma'am. Over to you, ma'am. Thank you.
Before Madam starts, I want to say a few things. Ma'am, thank you very much for accepting our invitation, and it was really wonderful that you have always guided us. You have visited our laboratory and you had given a very important suggestions to improve the laboratory facilities. I want to tell all the participants that the LD College of Engineering, the Applied Mechanics Department is going to organize FDP on confined masonry in the month of March. Now the code of confined masonry is going to come at any moment, and this will be the first course under GIAN. It's a global initiative of academic network. So under GIAN, Svetlana ma'am is going to coordinate the whole program, which is planned in the month of March, and we will tell you the exact dates of this training program. So thank you, ma'am, for accepting our invitation, and now it's over to you, ma'am.
Thank you very much, and good morning, everyone. Can you hear? Sorry.
Yes, ma'am. Yes, ma'am.
Good morning. Yeah, I think my microphone was muted. Can you hear me now?
Yes, ma'am. We can hear.
Okay, you. Let me start. First of all, good morning to everyone, and I hope that you are doing well. I would like to first congratulate the organizers and thank them for inviting me. And I think it is a great idea to do event like this in this difficult time when we are all confined at home, at our homes, and unable to function in a normal way due to the COVID pandemic. So I will start this lecture by providing an overview of the topics. So I will talk about basics of confined masonry, then seismic behavior of confined masonry buildings, then planning of confined masonry buildings in seismically prone areas, seismic analysis and design, and the performance of confined masonry buildings in past earthquakes. First of all, in introduction about confined masonry, I believe that most of you have heard or learned these fundamentals or know what confined masonry is, but anyways, let us start from the basic concepts. So it is a construction system where the walls are constructed, masonry walls are constructed first, and the reinforced concrete tie columns and tie beams are cut afterwards. This construction is most suitable for low and mid-rise buildings up to G+4, G+3, G+3, so 4 to 5 stories high. Key structural elements of a confined masonry buildings are masonry wall, then reinforced concrete vertical elements, which are called tie columns, and then horizontal elements, which are called tie beams. And also in India, it is proposed to use lintel bands. So those are not typical confined masonry elements, but are included and in Indian practice of just a moment. I'm getting some control. Okay, some request for control. Sorry, I hope that is okay. This is stop presenting. Is there any problem?
We can see the presentation.
Okay, because I'm getting message that somebody wants to control the presentation. Sorry about that.
Everything will be controlled from us, so just you can continue.
Okay, no problem, no problem. So, as I was saying, for the key elements constructing masonry building, look somewhat similar, like a combination to its combination of the elements of current masonry practice in India for seismically prone areas, such as bands. This lintel band is there, and then there is a roof band, which is called tie beam. That's what I want to say. And on the other hand, it also has elements of reinforced concrete frame construction. So, and these vertical elements look like columns, but they are not columns. We call them tie columns in confined masonry, as it is shown here. And I will explain the difference between these elements and columns in reinforced concrete construction. So looking at the plan view, it shows these black squares show the locations of tie columns, and now you can see a difference, clear difference between confined masonry system and the frame system. Because in the frame system, you would have a grid lines of columns, which would be in some regular pattern, but you can see that these tie columns are placed differently. So there are certain rules which are labeled here with one, for example, tie columns need to be provided at the wall ends. Then the second thing is that they need to provide it in their sections of the walls. Let's say these two exterior walls at the intersection, there are tie columns, and also interior wall and exterior wall. There is in the tie column there. Third one is that tie columns needs to provide it at the openings. And that means that they need to provide it at each side of doors or windows in most cases. And finally, they need to be provided in the middle of a wall which is long, let's say more than 8 meters long. So at every 4 meters, we need to have a tie column. So they're, in some sense, a form of reinforcement for masonry. they're definitely not columns in the same sense that they're columns in reinforced concrete construction. So in other words, confined masonry has some similarities with current Indian practice for construction of masonry in seismically prone areas. For example, this concept of bands. And then it is not shown here, there are vertical bars in some cases in high seismically prone areas in India. That is according to Indian standards such as IS 4326, and it is has been a practice for many years. Okay, so but the main difference, on the other hand, as I mentioned, there is a similarity between confined masonry and reinforced concrete frame construction, but there are key differences. One is in the construction sequence, and the other is, even more important, is different structural system. So frame system versus wall system. In terms of construction system, construction sequence, sorry, there is, in case of reinforced concrete frames, we first construct reinforced concrete elements and then walls, infill walls. In case of confined masonry, walls are being constructed first, followed by concrete elements. So this is the sequence of reinforced concrete frame construction, where we can have first the frame and then the masonry infills. Whereas in confined masonry, there is reinforcement in columns and in the, let's say, plinth band, but then the walls are constructed up to certain height, let's say story height, and then it is followed by the construction of these concrete elements. So I think this animation shows the difference clearly on a simple example. In terms of the structural system, looking at the top level drawings, on the left-hand side, we can see reinforced concrete moment frame, and on the right-hand side, confined masonry structure. So in a concrete frame, we have a relatively large size columns and beams, and then infill walls may be thinner than these elements, smaller size, smaller thickness than the column width, for example, or beam width. In confined masonry elements, wall thickness is the same as the size of tie columns and tie beams. So as a result, tie columns and tie beams are much smaller. They're just framing confined masonry, these walls, confining masonry walls. That's hence the name confined masonry. In terms of the structural or seismic behavior, in reinforced concrete frames with masonry infills, there are rigid connections between beams and columns, and then cut in this system, but the connection here is rigid. In confined masonry, all elements work together is a unique structure. So there is no, so these tie columns and tie beams are just reinforcement to masonry. Even though visually, once these buildings are constructed, there is a similarity in how they look like, appearance of these two systems. So in conclusion, confined masonry is a load-bearing wall system, while infill walls in reinforced concrete frames are non-load-bearing elements, and very often, unfortunately, are not taken into account in the design, and they should be taken into account. And confined masonry, I have not seen, but according to information I have, is that confined masonry is known as a double bearing wall system in some areas of India, for example, Bhuj area, where it was constructed after the 2001 Bhuj earthquake. But this practice is mostly performed in rural areas and without any given guidelines or specific provisions for these for layout and detailing of these structures. But it is in a sequence, in terms of sequence of construction, it falls into a category of confined masonry. So beginnings of confined masonry are about 200 years, 120 years ago. It started, the first mention of confined masonry in the modern world was the earthquake. It had a magnitude of 7.2 and a very significant death toll. The more than 70,000 people died in the earthquake. So after the earthquake, it was observed in that area that confined masonry buildings existed and they survived the earthquake. So it is not known who actually came up with the idea of confined masonry, but it was identified after this earthquake as earthquake resistant or technology that provides better earthquake safety of our buildings after an earthquake. So after this earthquake, and the next masonry was in like Chile, Colombia since 1930s, and in Mexico since 1940s. So Latin America is the second region of the world where this construction technology has been used for many years, more than around 100 years right now, and it performed really well in earthquakes, because Latin America is in general a region of very high seismically prone, many high seismic hazard, or there are many earthquakes in that region. For example, I will be talking about Chile earthquake, or examples from Chile earthquake. That in Chile, statistically, every 10 years there is an earthquake of magnitude 6 or higher, and it is a pretty small and densely populated country. So there are no regions where there are no buildings. So all their buildings are exposed to earthquakes every 10 years, to really significant earthquakes. So this is conclusion that confined masonry has been practiced in several countries or regions with high seismic risk. Primarily, I would say some parts of Europe, then Middle East, Iran, for example, South Asia. Indonesia is one of the countries where it has been used, and in the Far East, China. In China, it has been used also for a relatively long time, and it has been part of Chinese codes. So these are some examples of confined masonry in Indonesia. In Indonesia, for example, they use confined masonry mostly for single-story housing, and construct a very thin half brick thick wall, and for confined masonry buildings. Indonesia is also country with high seismic hazard, many frequent earthquakes, and confined masonry buildings perform well in those earthquakes. In Chile, this is at the end of this presentation or this lecture, I will talk about performance of confined masonry buildings in a Chile earthquake. Here is an example again of low-rise confined masonry buildings, which are buildings in a row, so to speak. You see that they're all connected. That is, they also have individual buildings among low-rise buildings. These are some examples from Mexico, and this is with hollow concrete blocks. But you can see that it is confined masonry because you can the vertical this reinforcement in tie columns. That's how we can tell it's confined masonry. These are some examples from Chile also, where they are building, they're using confined masonry for apartment buildings, mid-rise apartment buildings, something like G+3, G+4. So these are examples of confined masonry from Chile. And similarly in Mexico, I didn't show photographs here. They also show they also use confined masonry for apartment buildings. In India, I would like to say how the initiative started. It was initiated by structural engineers, earthquake engineers. At least I would talk about engineered aspects of confined masonry. I mentioned earlier that there are some rural applications, but here I'm talking about more formal applications and initiative to use confined masonry in India in a formal way. Let's say through codes, as similar to other construction technologies like concrete, steel, and all that. So the reason for proposing use of confined masonry in India is relatively poor performance of some reinforced concrete frames with masonry infills in the 2001 Bhuj earthquake, and probably some other earthquakes, but certainly the initiative started after the Bhuj earthquake. So it started in Gujarat. So confined masonry was first identified and as an alternative to reinforced concrete frames with masonry infills in 2005 by Professor Sudhir Jain in the paper Indian Earthquake Problem, which was published in Current Science journal. So, and subsequently in 2007, National Information Center for Earthquake Engineering, NICE, at IIT Kanpur, published first confined masonry publication, which I authored. It was a monograph that was in 2007, and in 2009 another publication illustrating construction of confined masonry buildings by Tom Schacher was also published by NICE. And then subsequently at Gandhinagar, at IIT Gandhinagar campus in Palaj village, which I believe attendants from Ahmedabad are familiar with the location and maybe visited campus as well. In the planning stage, since it was a brand new campus, in planning stage, it was envisaged to use confined masonry for construction of housing and housing for the faculty and staff. That is shown here on the left. Those are 30 blocks, Howdy blocks, and then initially 6 student hostels. Later on, 6 more hostels were also constructed in the confined masonry, but this is the first. This was the first step. The construction took place between 2013 and 2015, and it is still going on. So this is on the banks of Sabarmati River, and here I show some photographs. So this is, as I said, the first group of confined masonry buildings on this campus. 36 buildings in total, and currently, right now, at this moment, there are more than, I would say, 45 to 50 confined masonry buildings. Even the residence of the director of IIT Gandhinagar was also constructed in confined masonry. So here is the Gandhinagar. You probably know him or know of him, Professor Sudhir Jain. He is the one who proposed the use of confined masonry on this campus, and he had a very hard time of explaining what confined masonry is to concerned engineers and anybody implementing the project. So he arranged for construction of a sample wall to illustrate demonstrate how confined masonry construction looks like, since there were no other examples. These photographs was taken in 2013, before the construction of campus started. It was all the initial campus in Chankeda. So these are plans. This is a plan of a typical confined masonry hostel at IIT Gandhinagar. You can see it looks similar to any other hostel anywhere else in India. But the details of construction reveal that it is confined masonry. In this campus, instead of clay bricks, fly ash bricks were used because of inadequate strength or quality of locally available bricks. And so that is the masonry walls were built using the specified strength was 7.5 megapascals or 75 kilograms per centimeter square, and the mortar mix was 1/6 cement lime sand, if you're interested. And then these are confining elements, tie columns, so you can see that it was confined masonry construction. And you can see example of formwork. I'm not going to show construction photos, but the publication illustrates the construction of all these buildings at IIT Gandhinagar campus, and it can be downloaded free of charge. So I will show it at the end of presentation. So this is construction of hostels. So you can see confined elements, and then you can see after plastering. This is construction. These are typical housing blocks. That is G+2, and they were also constructed in confined masonry. And this is after construction. This is actually housing and hostels, just illustrating both types of confined masonry construction after they have been completed. So so that would be just introduction. Now, second is the very important question: how confined masonry behaves in earthquakes or when subjected to earthquake loading. How does it behave and how does it fail when it comes to it? So if we have a confined masonry wall, which is subjected to, of course, gravity loading, and then some lateral loading, let's say induced by earthquakes, initially the damage would start by cracking of masonry inside masonry walls, within masonry walls. So this is so-called diagonal cracking, which is caused by shear effect or exceeding shear strength of masonry. And in the next stage, with the increasing loading, the cracks would propagate into confining elements, tie columns specifically. And with the further increase of loading, there would be a complete deep cracking through these tie columns. and through the walls, as you can see. And in this diagram, this is something that is known as a backbone curve in world of earthquake engineering, where we have lateral force or shear force versus horizontal displacement due to this loading. And you can see this point 1, which is here. So initially the wall behaves elastically until the cracking starts. Then after the cracking, there is a change in the slope of this curve, which is due to cracking. So this is a drop in stiffness, drop or decrease in stiffness. And at the point when cracking extends into tie columns, that is a point where a confined masonry wall has achieved the maximum strength. And after that, it goes downwards the failure. And failure is denoted as this point 3, which does not mean collapse, but it means a failure of the structure in engineering terms. So what I would like to emphasize here is the difference between these points 1 and 2. If we had a unreinforced masonry wall, we would stop at point 1 because there is nothing that could increase the strength of this structure after the masonry has cracked extensively. However, due to the presence of these tie columns, it is possible to further increase the strength of this wall to up to 0.2, and that difference is about 25%. So it is not twice, it is 25%. But more important than that percentage, by how much we increase the strength by using confined masonry, it is the fact that these confining elements prevent sudden and brittle failure, which is characteristic for unreinforced masonry. So they increase ductility, or the ability of this structure to deform and of course crack and get damaged, but not fail or collapse in a similar manner as unreinforced masonry. So these are improvements in confined masonry compared to unreinforced masonry. These are experimental, some evidence from experimental studies. Confined masonry has been extensively tested, not necessarily in Asia, but let's say in Latin American countries and in Europe. It has been tested, numerous research studies have been performed, starting from, I would say, 1960s. So in the last 60 years, they have been related to the result of testing in Mexico. And you can see here how deep the cracks are. So that would be the final stage. You can see that crack is gone thoroughly through tie columns. And on the left-hand side, these are some tests in Japan, and they only show how cracking pattern looks like. You can see these diagonal cracks, and then you can see cracks in tie columns at the tops and the bottoms of tie columns, simply as extension of these diagonal cracks in the walls. These are some tests from Peru. They, for example, studied the effect of different width of tie columns on the performance of confined masonry walls. They tried with the 20 centimeter wide tie columns, and then they tried also, they did another study on 40 centimeter wide tie columns, and they try to find the optimal masonry walls. You can see that in both cases there is a diagonal crack, and you can see here it is like a diagonal strut that forms between the corners of a confined masonry wall. And in the case of 40 centimeter wide column, there was a distinct separation also along the interface between the wall and tie columns. So in multi-story building, the confined masonry multi-story buildings subjected to earthquake loading, the studies and evidence from earthquakes has shown that that the maximum damage occurs at the ground floor level, at the base of the building. Why is it so? Well, simply this is coming from the nature of earthquake loading, and even the way we as engineers design these buildings, and the codes prescribe the design or application of forces, is that the forces are accumulating from the top to the bottom. So the largest forces are at the base of the building, and also, of course, bending moments. But here we are talking about construction typology, which is predominantly affected by shear. So here you can see cracks at the base of the building, and those cracks are caused by the fact that that masonry strength has been exceeded at this level. So this cannot be prevented. It is only a matter at which level of earthquake or earthquake intensity or these seismic forces this would occur. So this is the critical region for confined masonry. It is good to know because of construction practice. If we have a multi-story building, I don't want to say that we don't care how the upper floors are constructed, but this means that the construction at the bottom portion of the building, lower floors, is most important. Is critical actually. Here is an example of a shaking table study of a model of a confined masonry building in Mexico. You can see it has a door, windows, and it was done at UNAM, that is the largest government university in Mexico. It has 250,000 students in Mexico City. And the researchers are Professor Sergio Alcocer and his colleagues at UNAM. It was done about 20 years ago. Oops. Oh, unfortunately, let me see if this will work. It will. Okay. So you can see here the pattern of behavior. This is the test for this building. So the building did not collapse, but it was significantly damaged at the ground floor level. So there was no further, because even further exposure to even more intense earthquake excitation or simulated earthquake would not cause a failure. It would just cause further deepening of the cracks. This building model was subjected to very strong shaking. And this study was explained in a paper published at the 13th World Conference of Earthquake Engineering. I listed the references at the end of this presentation in case you are interested. And other studies done in Mexico, Slovenia, other countries, they show similar or same behavior for our multi-story confined masonry buildings. So what are the key parameters or factors that influence seismic response of confined masonry walls and confined masonry structures? I would say they're similar to other structural systems, other masonry structural systems. I would say I would talk about masonry technologies, particularly not reinforced concrete. One of them is quality and mechanical properties of masonry. Masonry is a building material. So in simple words, I didn't try this, but if you have a poor strength of masonry, confined masonry, the fact that you're using confined masonry is going to help up to a certain extent, but there is no magic. Minimum strength of masonry materials have to be achieved. Then the second factor is size and location of openings, meaning doors and windows. Then the third one is size and meaning dimensions and detailing of reinforcement in confining elements, particularly tie columns, so vertical elements. And the last one is toothing, that is interface between masonry walls and tie columns. In terms of building materials, there is really no limit which materials can be used. In some countries, I know that even adobe blocks were used in combination with confined masonry. But it all depends what are we building, what are we designing. Is it a single-story building, or it is a single-family house, or it is a 4-story apartment building? The required strength will depend on the size of the building or the height, particularly. So both bricks and blocks can be used for confined masonry. It is the fact that clay bricks may have very low strength in some parts of India. For that reason, for example, at IIT Gandhinagar campus, fly ash bricks were used. So there is always an alternative. There is in recent past, there has been a significant concern related to the use of hollow concrete blocks in confined masonry construction due to very poor strength of hollow concrete blocks in some countries. This was particularly observed in Haiti, but also in other countries, let's say in African countries, in Nepal as well. So so that is the conclusion is any material can be used, any type of masonry unit, bricks or blocks can be used, provided that they have some minimum strength, which is usually prescribed by the codes. In Latin America, as you will see in the slides, and actually I should go to the next slide. In Latin America, actually, they're using multi-perforated clay blocks. So this is a section of those blocks. This is under B. And under A are hollow units. This is some just recommendation in terms of the dimensions of these hollow units, primarily concrete blocks, because there is a concern that these blocks are very vulnerable to earthquake effects. So international guidelines, one of them is I'm referring to it as ERI 2011. That was a guideline developed by a group of experts from 13 countries, which have combined expertise and knowledge from their countries and their codes related to confined masonry, and propose the minimum requirements for confined masonry that are generally recommended for countries which don't use confined masonry and would like to use it. So let's put it that way. So in terms of materials, minimum compressive strength for bricks was 4 MPa, which is similar to the requirement of Indian standard IS 1905, which is 3.5 MPa. But for blocks, 5 MPa was specified as a minimum. So that is one thing. The other is, I already explained this, is that there are rules related to the layout, to the spacing of tie columns, to the location of these tie columns, and they have to be followed. These rules may sound prescriptive, but they are based on studies and also on experience from past earthquakes. So there should not be cutting corners in provision of these tie columns. I've already explained, this slide was shown before, but I'm showing it here because this is in the context of an important factor that influences the behavior of confined masonry buildings in earthquakes. And one of the key aspects is the provision of tie columns at the openings, such as windows and doors, among others. So this is regarding size and location of openings. In that same guide, in the ERI 2011, again, it is free of charge. I will show where you can, the title and where you can download it. I'm sorry I didn't make a reference to it. But there is a recommendation regarding, let's say, size of openings. So if an opening is of such a size that it takes more than 10% of the area of a confined masonry panel, that means, or confined masonry wall, that means wall that is a masonry wall enclosed by tie columns and tie beams. So that wall is actually not considered to be confined unless a confinement is provided at the ends of this, on the side, at the jambs of this opening. That is one rule, and that is the only way. So in other words, look at this left and right confined masonry wall. So these two walls are confined, and this one shown under A would be unconfined. What does it mean? The wall would exist, no question, but it would not contribute to resisting seismic forces. That is all. And the question could be whether we could provide some nominal reinforcement here, which is a good practice around vertical and also horizontal direction. Yes, but unless you provide reinforcement that is required for tie columns, it would not be considered as confined just because one bar is provided on each side. That is not considered as confinement in the sense of confined masonry. So here are some examples from earthquakes both are from Mexico, where confining elements were not provided at the ends of openings. They're provided here in the middle. And that is probably because there is a wall in the other direction here. But these buildings did not collapse, but were badly damaged. That is the consequence of this. And I'm sure that this element also helped in a sense, because there was a cracking crossing this element, but it is not as effective as if there were elements on each side of this opening, on each jump. And this is similar photo. Just again, there was no confining element at the opening, but it was just at somewhere in the middle. So detailing of reinforced confining elements, the key objectives or goals of detailings are that these confining elements need to be designed to prevent or delay propagation of cracks from the walls into these elements during an earthquake. So proper reinforcement in this vertical element, specifically tie columns, is very important. Here is an example from 2010 Chile earthquake. It is a wall, confined masonry wall. You can see this on the left side is a tie column, and this wall was constructed using those multi-perforated blocks. But if you look at the detail of this tie column at the base, I'll show you now the photograph. So you can see how this reinforcement buckled. So concrete has spalled completely and the reinforcement has buckled. In Chile, they used very small size of ties, and in some cases, and at a relatively large spacing. And that caused damage of some of the confined masonry in some buildings. You can also see that these multi-perforated blocks crushed completely in this area. This is very typical for confined masonry and for masonry in general, to have significant damage at the base of the wall. In this, we call it toe. So it is called toe crushing. So what can be done to prevent or delay this type of damage? Some guidelines, again, this is from the ERI guideline, propose a closer spacing of ties in tie columns in the top and bottom portions. And if, let's say, the spacing is normally 200 millimeters, then in these regions, it is 100 millimeters. Other option that many countries accept and have adopted actually is to use uniform spacing, and I believe that will be the case with India, with the draft Indian masonry standard, is that use a smaller spacing, something in between, something like 150 millimeters uniform spacing, and that is already better than 200 and would be compromise between these two. So in any case, it is important to emphasize the top and bottom regions of the tie columns are the critical locations where maximum care should be paid to care and attention during construction. So here is another example from Chile. You can see buckled. This is a wall with the concrete blocks, confined masonry walls at the base of a 3-story building. And again, you can see a detail of buckled reinforcement in tie columns due to small size of ties and not enough sufficiently closely spaced. So this is again illustration of this. I think that is it. This is another example from Chile, where actually the tie columns were provided at the openings. This looks like a brick. It is a brick building, and this look like bricks at the ends. But what they did is they used they formed it to look like bricks, but in reality these are tie columns. So this performed well. There is a crack, but not extensive damage as it could be. I believe this was a 4-story building and subjected to very significant shaking in the 2010 earthquake. The photographs from Chile I'm showing you, and I will say a few words about these earthquakes. It was a magnitude 8.8. So significantly stronger than the 2001 Buj earthquake, which was also very strong. Yeah. So the last topic, And that is the one where engineers and researchers in various countries do not agree 100%, and that is toothing. Toothing is a way to provide interface between masonry walls and concrete. Because one of the assumptions of confined masonry is that there is integral action between masonry and concrete due to toothing. So toothing is achieved by providing these bricks as in zigzag manner, as you can see here, like a teeth. And you can see that the size of this toothing is, let's say, up to, depending for bricks, up to 5 centimeters. And that is one way of achieving that. And then when concrete is poured, it will bind together, or there will be bond between masonry and concrete. Experience from construction at IIT Gandhinagar showed that it is not easy to achieve, especially at the beginning. And also it is required to construct a smaller portion of the wall, let's say up to mid-story height, in order to be able, and then pour concrete in order to achieve proper toothing. In some countries, like Mexico, for example, they use, because they use blocks, they don't use bricks anymore at all for masonry construction. They use these multi-perforated blocks. So it is very difficult to achieve toothing with the blocks. So in Mexican code, it is allowed not to have toothing. So you have straight edge, straight interface, but then there is a provision of horizontal reinforcement at certain spacing of certain length and spacing along the wall height. Similar provision exists in European code, in Eurocode. So these are two alternatives. Here is an example from Mexico. You can see multi-perforated blocks, and you can see that straight edge without toothing. What is interesting also to observe is that in Mexico, they make prefabricated reinforcement cages for confined masonry. So you can order cages and then cut them at the site to the size that you need for a story height and all that. And then additional ties can be placed separately. So if the tie spacing is not sufficient, they add ties, but all the rest is provided as a package. As these are welded. I believe the ties are welded, or I think they're just somewhat tied, somewhat connected. I'm not sure 100%. So the other option is this is photograph from Chile, where they use bricks, and so you can see toothing plus this horizontal reinforcement. That is also interesting. And also what is interesting is that toothing is provided for 2 bricks, 2 brick high, and then there will be another 2 bricks on the same level. Yeah. This is from IIT Gandhinagar. You can see toothing, how it was done for each brick. They had the toothing, and this is at the wall intersection. So the studies done in India, a very significant study was done at IIT Kanpur by Professor Durgesh Rai, and now also Professor Vaib, who is at IIT Kanpur, and Professor Vaibhav Singhal, who is at IIT Patna. So they studied they studied several confined masonry walls. In any case, they studied the effect of toothing. So on the left-hand side, you see wall without toothing, and on the right-hand side, you can see wall with toothing. These walls were subjected to in plane and also out-of-plane seismic loading. So it was a very interesting study. So it can be clearly seen that there is a difference in behavior. However, the conclusion was that even the wall without tooting did not perform dramatically bad. They didn't collapse compared to the other wall, but the damage pattern and the behavior of wall with tooting was superior. So tooting has clear benefits. In the case of IIT Kanpur study, in this study, there was no horizontal reinforcement provided. So it was simply without any tooting, straight edge. So this is about behavior and important factors. I would say certainly reinforcement detailing in tie columns is very important, and also the quality of masonry. The third is planning of confined. The third topic is planning of confined masonry building, and here I would maybe bring up some rules which are similar to other, again, wall systems, masonry or concrete. I would say they would be applicable to other systems, other technologies. So I will talk about two aspects of this planning in, of course, seismically prone areas. One is building configuration and the other is wall layout. So in terms of building configuration, I know that oftentimes we have irregular buildings, either in terms of the plan shape, so like this U-shaped plan, or in terms of layout of the wall, but we'll discuss that now. Talking about plan shape, ideally, in an ideal world, buildings should have a regular plan. But many, particularly masonry buildings, are non-engineered buildings, and owners and builders are not even familiar that there should be some regularity in plans. And also there is construction is going on over time. So there are horizontal extensions of an, so it is not possible to have a regular plan. In that case, so here I would like to bring up that these drawings, illustrations, were taken or excerpted from a publication which I co-authored with Professor K.M. Mitra, who is an architect, and we published detailed, I would say, confined masonry guideline or a primer for engineers and also architects, which was published by NICE in 2018. My first publication that I published with NICE was in 2007, but this is much improved, I would say, and a larger, more comprehensive version of that publication. So this slide illustrates acceptable irregularity. So if you cannot make a fully irregular plan, what is acceptable? So it is acceptable to say have a certain percentage, let's say 15% of the length. It could be offset. This one part of the building could be offset with regards to the other, and this is showing L-shaped, U-shaped, these different options which are possible for let's say low-rise buildings particularly. So another option is to create seismic gap. So what is seismic gap? That is spacing between adjacent buildings or parts of the buildings, which, if it is provided, has a result that these parts of the buildings behave independently from each other during an earthquake. So that is also a possibility to create this gap. But if there is a gap, that means that you need two walls and in the certain location, so it would have cost implications, particularly for low-rise buildings. So the reason we have gap, particularly in taller buildings like apartment buildings, is to prevent so-called pounding or crashing of buildings against each other. If there is no seismic gap, these two buildings, like shown on the left, these two buildings would pound. So the lower buildings would be stiffer, and would cause a damage in the taller building in the top level, let's say at the third floor level in this case, but both buildings would be damaged. So therefore, there is a need to have a gap, as shown on the right-hand side, because during an earthquake, we don't know whether these buildings are going to move towards each other or away from each other. They're going to move in both directions, isn't it so? So there are some rules in these publications. We suggested also some sizes of the gaps and recommended the gaps size. And these are some examples of pounding or how pounding would look like in if three buildings are constructed next to each other with. So this applies to any other type of construction, not only to confined masonry. One thing that is important for confined masonry and for any masonry buildings is to have continuous walls. So to avoid the situation shown on the left, and to have the continuous walls like shown on the right, because those walls would be effective in resisting seismic forces. So this green is showing yes. Lastly, this is something that I believe some architects, maybe engineers, would be tempted to implement in India in case of confined masonry, and that is a so-called hybrid system. In reinforced concrete frames in India, there are situations where actually many examples of buildings with open ground floor. In any Indian city, it is possible to find these buildings. Now, in confined masonry, it is ideal to have continuous walls from ground to roof. That is the idea. But the question is then, can it be, how can this be constructed in confined masonry? Well, it cannot be constructed. This is known as hybrid system because if there is concrete at the ground floor, this ground floor would work as a frame, and the upper floors would work as a masonry wall structure. So one has to be really careful with the design or any difference in design between ground floor and upper floors in a confined masonry, and that will be addressed by the Indian code for confined masonry. The second important topic is wall layout. Again, ideally, we like to have a symmetrical layout of the walls, because if we have symmetrical layout, we avoid torsional or effects or twisting of a building. However, if we move one of the walls off so that it is not symmetrical, the layout is no longer symmetrical, there will be some eccentricity between the center of the center of the building floor plan, which is center of mass, and the center of rigidity, which is related to the walls. So if we keep moving stiffness or keep moving longer walls on this side, center of rigidity would move on that side. So what we are suggesting is to have less than 10% offset or different eccentricity between the center of mass and center of rigidity. Of course, engineering calculations are needed to calculate that. That could be just based on the areas of the walls, so it does not require more complex calculations, but that is ideal, certainly. And I understand it is not possible in all cases. This is just a recommendation. Of course, with engineer design, any torsional effects can be taken care of through design. What is important for any masonry structure, including confined masonry, is to have at least 2 parallel lines of walls in 2 directions, and that is what is shown here. So that there are two lines of the walls, and secondly, if there are walls with openings, that the length of the total length of the walls along one grid line is at least equal to 1/2 of the length of that side of the building. Let's say this is a length L, so that this single wall, there is a single wall, its length need to be greater than 0.5 L, and similarly some of these two lengths for W2 and W3 needs to be also greater than 0.5 L. So these are some rules. There are more, and in that publication you can find some more rules. Seismic analysis and design, I'm not going to talk about this in detail, but I will just explain a few approaches which are commonly used. One is equivalent frame model, that is for engineered analysis of confined masonry buildings. And the other is strat and time model. And the third is simplified method. In fact, I will talk in detail about simplified method, but I will briefly explain these first 2 methods. So in equivalent frame model, it consists of idealizing a confined masonry wall or as an equivalent frame. Let's say on the left-hand side you have the actual wall, and it has confining elements on each side. So all these walls are confined masonry walls, even though those round openings. So we have, in the other words, we have 3 confined masonry walls. We can simulate by a column, which is called wide column. So this method is sometimes called wide column model. So, and that column is located at the center of the wall, and it has properties of masonry. That column has properties of masonry and concrete. It is like a transformed section. And similarly, these other 2 walls are shown as these vertical black lines. Those are wide columns. And then horizontal lines are showing basically beams. The bold blue lines are showing rigid beams, which are simulating the effect of interaction between the wall and the floor slab. So they're not real elements. They're simulated elements which have high stiffness. The red lines are showing the actual beams, actual slabs, actually portions of the slabs. So entire building can be modeled using this equivalent frame model in 2D or 3D. And that is what is done for engineering analysis, let's say for seismic analysis. The other method or model is a strat and time model, where a confined masonry wall is modeled as a truss. So on the left-hand side, you can see an actual confined masonry wall, and on the right-hand side, you can see a truss. So truss members are clearly those tie columns, and you can see on the left-hand side tie column shown with the blue dashed lines, and on the right-hand side you're see tie columns shown with green line, solid line. So the difference, why are they shown differently? Because due to seismic loading, let's say acting from left to right, this right column, the tie column, would be subjected to tension, and it is so-called tie. Whereas the right-hand side tie column would be subjected to compression, and these compression elements are called struts. So in other words, reinforced concrete confining elements can be either struts or ties, depending whether they're under tension or compression, while masonry wall will always be modeled as a strut, because masonry is assumed to only take compression. What is also important is to note the nodes between these adjacent truss elements. So these are pins. So in confined masonry, we don't have rigid connections. We don't assume that there is any moment transfer between this tie column, vertical tie column, and horizontal tie beam. That's why this big black dots or circles are shown. So this is also possible, and it's particularly suitable for walls with openings. Simplified method is based on idealized distribution of lateral seismic forces in shear wall structures with rigid diaphragms. Shear strength, it is assumed that shear strength of all walls when put together exceeds the seismic force that acts at that level. So it will be more clear when I show the drawing. So let us look at this plan or elevation of the building. So if we have forces applied at these different story levels, so shear force Vx at any story level is equal to the sum of forces above that level, isn't it? That level. So, and then that story shear force is distributed to different walls at that level. Normally in masonry structures or in wall structures, we are looking at the force at the ground floor level, because that's where the forces are the largest. If the distribution of walls is regular along the building height. So here is the plan of, very simple plan of a building with 3 walls. And what we assume in this simplified method is a rigid diaphragm. That means that all walls, if they're subjected to the seismic force, the whole diaphragm or floor will move together like a rigid body. That means that all these 3 walls will have equal displacement. And we model the walls as horizontal springs. So springs, that means that they have their own stiffness. So if you have a wall that is longest of all, its stiffness is going to be the largest. So this is the largest stiffness, this is the second largest, this may be the smallest. So distribution of forces in this of this story force to these 3 walls will be proportional to their stiffness. So in this, if this is a wall we are looking at, this is a force in that walls. So it is calculated because it is a spring assumption. So force in the spring is equal to the stiffness times displacement. And at the same time, this force is proportional to stiffness of individual wall that wall, which I showed circled, relative to the stiffness of all walls in that direction. Okay, so we can maybe forget about this first equation and just use the second one, which sounds simplest and maybe less scary. So how do we calculate stiffness? We are assuming that confined masonry buildings behave in shear dominant mechanism. Therefore, stiffness, for their stiffness, we can only consider shear stiffness. And shear stiffness, for those of you who are engineering students or engineers, you know how shear stiffness is calculated. This is a product of modules of rigidity. This is some factor that takes into account aspect ratio, so it is just non-numerical value. This is area, cross-sectional area of the wall, and this is the height of the wall. So if we if all these other things are the same between the walls, so let's say all walls have the same height, we have a certain story height, 3 meters, all walls are made of the same masonry, therefore these modules of rigidity is equal, modulus of elasticity, modulus of rigidity is equal, and this F factor, let's just forget about it, let's say it is equal to 1. Therefore, the stiffness of the walls would be proportional to its area, cross-sectional area. So therefore, we can assume that if we have a wall with the cross-section meaning length of the wall times its thickness, and that the force, the resistance of that wall is equal to the shear strength of the wall times the area of the wall, and then again times this F factor, which takes into account height to length ratio of the wall. I don't have here equation for masonry shear resistance, but in the proposed Indian code, the equation is a function, or the masonry shear resistance is the function of the compressive strength of masonry. So there is a distinct equation for that. So in any case, if again we forget about this factor F, what we are showing here is simply average shear stress. Shear stress is equal to force divided by area. Therefore, force is equal to stress times area. So that is how we calculate that. And this is F factors, F value, which are obtained through some studies in Mexico, and equal to 1, height to length ratio is less than 1.33, or it is a function of length and height of the wall when this ratio is greater than 1.33. So for the basic purposes, let us assume it is equal to 1. So in here we come to the factor, which a very important indicator and of seismic safety, which is easy to determine and use in practice. It is wall index or wall density. So what is it? It is the area, the sum of cross-sectional areas of all walls in one direction, one principal direction, let's say vertical or horizontal, divided by the plan area, floor plan area for that same building. So you can see here, AW is the sum of areas of all these walls, and A sub P is the floor plan area. And this ratio would be wall index per floor. So we can easily determine it for any building once we know the the thickness of the walls and the length of the walls. What is important is to only consider the walls that are confined. Remember, we talked about the walls with the large openings which are not confined. They would not be considered in this calculation. And for every building, we can determine for any building at a specific site, let's say Burj, Delhi, Ahmedabad, we can determine the required wall index depending on the number of stories. So if you have more stories, we need more walls. It makes sense because the seismic force at the ground floor would be much higher, isn't it so? So therefore, the required index for buildings is equal to the number of stories times the wall index per floor. And so these are derivations how it was done for India. So we have seismic base shear force, which is equal to the coefficient, seismic coefficient times the seismic weight. And through derivations, we can obtain the required wall index for the whole building, which takes into account the number of stores and stories. N, let's say we have G+2 building, then N would be 3. And the seismic coefficient, which depends on the seismicity, the seismic zone, and so on. W is the average floor weight, which you can be calculated. Gamma M is the factor for material factor for masonry, which is proposed to be 2 for Indian standard, and this is simply the similar factor like we have in a concrete design, where you have to reduce the FCK, you have to multiply by 0.667. Here, this factor of 2 means that you are basically taking 0.5 times of the shear strength. Okay. So I think my battery is running on. So I'll just show this example. So if you have, for example, seismic zone 3 of India, and we assume 7.5 MPa bricks and type M1 mortar, in this publication, for example, of confined masonry by Brzev and Mitra, determine what is the required wall index per floor. So for Ahmedabad, which is in seismic zone 3, it would be 1% per floor. So if you want to construct a single-story building, that would be 1%. So if you look at this campus at IIT Gandhinagar and this building, which is a hostel, G+3, we have N is 4, and the required wall index per floor is 1% or 0.01. Therefore, this results in 4% required wall index at the ground floor, because this is a G+3 building. So it's very simple. It is not sufficient for a design of confined masonry buildings, but it is very good for preliminary design and planning. So conclusions related to wall index is that it is a very relevant concept for all load-bearing structures, and even reinforced concrete structures with masonry infills when reinforced concrete frame elements are weak. And that is example of the 2015 Gorkha, Nepal earthquake. We published a paper related to that. I listed the paper at the end, which showed that if reinforced concrete frames with infills perform similar to confined masonry buildings, then wall index is very important. So that means if frame elements are very small, like the ones that are exist in Nepal, they basically behave like a wall structures. But in any case, for the context, Indian context and confined masonry, the wall index and its application is very important for improving seismic safety, at least at the preliminary stage of the design. So that is all about wall index. Last topic is seismic design of confined masonry walls. I would like to say that confined masonry walls are load bearing. I think I'm running out of time, so I'll finish with this topic. Masonry walls and tie columns act like a composite section or structure. Transform section properties are used for analysis and design, and strain distribution across the section is linear. So plane sections remain plane. That is assumption for beams or any flexural elements. So design of confined masonry walls for axial load and bending is as proposed by the Indian the draft Indian confined masonry standard is based on the interaction diagrams, P and M interaction diagram, which will be with their equations for constructing in lower bottom right corner. You can see that interaction diagram. So it can determine the required masonry strength or resistance for a specific level of axial load. So what is assumed here, you have a cross section of a masonry wall, and you can see the strain distribution and then distribution of internal forces. You can see compression on this side, compression stresses, and tension stresses on the other side. And that is the basis for developing the equations of this interaction diagram. And the last part of or aspect that needs very important aspect for design is the shear resistance. I'm not included the equation here. You will see, or maybe you have seen already the code, the proposed code. There is equation for shear resistance, which is a function of the area of the wall and the shear strength. What we said, that Vm times the area, and also the level of axial gravity loading. What is important to emphasize that equation is based on this minimum strength, which is corresponding to the beginning of cracking in masonry, not the maximum strength, which takes advantage of confining elements. That is important, and the equation is very simple, easy to use. So I have to take a break.
Hello, ma'am. Ma'am, I think there is a problem in your network. Your voice is not clear. We are not getting your voice. Okay.
Ma'am has taken break, I think.
Okay.
Hello. Hello.
Yes, sir. Yes, sir.
I'm calling Svetlana, ma'am.
Can you hear me? Can you see me?
Yes, ma'am.
Okay, so I'm almost done. Sorry, I had a problem with the power supply. I apologize, and I had to disconnect for that reason. So I have finished practically. I just want to show one more slide regarding this proposed code. So let me just start sharing. Let's see. Apologize for that. Okay. So the code, can you hear me?
Yes, ma'am. We can hear you.
Thank you. So, so this the detailed, I would say, guidelines and provisions for confined masonry are provided in draft Indian standard for design of confined masonry buildings, which is currently under review. The latest version was submitted in June 2020. I'm a part of the group that, along with Professor Durgesh Rai, Professor Vaibhav Singhal, Professor Sudhir Jain, who has proposed the code, and it has been discussed, and useful comments were obtained from the members of the CED 39 committee. So it is currently under review, and it is expected, as Professor Sanghvi mentioned, to be and Professor Murthy earlier on, to be adopted, finally approved sometime in 2021, and it will finally set rules for or enable construction, design, and construction of confined masonry according to Indian standard, and avoid lots of confusion, which is of course possible when there are no clear guidelines. So there are many different guidelines in a sense. What I wanted to say at the end regarding confined masonry, what I presented now in terms of the design is based on the ultimate limit stage design. So it is using similar methodology that like we would use for reinforced concrete and steel buildings. It does have a section on working stress design, but it is really very from IS 1905, and it's a different type of code altogether. Of course, IS 1905 is a code for masonry building. It has lots of useful information, but this one is specifically for confined masonry. So I have some slides regarding performance of confined masonry buildings in past earthquakes. I think I would leave that for you. I've gone over time. It takes time to explain, and I had some problems with auditing, so it was I was a little bit disturbed during the presentation. I'm not sure what was the problem, maybe on my side, but anyways, I would stop the presentation. What I would like to show you is just a few useful resources at the end, and that is it. You can take a look at those slides. You have them in the notes. So I included, so conclusions are that confined masonry is a viable construction technology for low and mid-rise buildings in earthquake-prone areas of India and other countries. Confined masonry buildings have performed well in earthquakes, provided that certain rules regarding design and construction have been followed. And certainly confined masonry is a more forgiving system compared to reinforced concrete frame construction in terms of performance, where collapse is prevented. So damage is not avoided. Damage is expected in major earthquakes, certainly, but collapse is the one that is prevented. So I included a number of references for your use and interest. But what I want to say is you have also some free publications like this ERI guideline. It is available free of charge on the ERI's website, and then if you are interested in confined masonry and let's say you're not familiar, you would like to learn the basics, there is a publication which is available through AICTE. It is not available free of charge on the website. It comes at some cost for now, but it was developed with the support of BMTPC, Indian Institute of Technology, Gandhinagar, and NICE. And certainly, finally, there is a publication, I think, Gandhinagar campus construction. Electronic version is available free of charge on this site. It shows describes challenges, construction features, and how that campus has been constructed. I acknowledge my colleagues, many colleagues I worked with from Latin American countries like Mexico, Dr. Juan Jose Perez Gavilan, and a number of colleagues I worked with. And so thank you. Any questions? I skipped a few slides from performance of confined masonry buildings in Chile earthquake, but I did show them anyways, some other photographs I showed throughout this presentation. So, and thank you very much. If you can hear me and if you have any questions, I'll be more than happy to either explain something that I already said, or if you have anything related to confined masonry you would like to ask, I'd be happy to.
Thank you, madam. It was a really nice session, and now the forum is open for the questions. Participants, please, you can ask questions, and I request Professor Bansal, to unmute participants.
Yeah, participants are allowed to unmute.
Yeah, Sunil Kumar, you can ask question. Patel Jaldeep Kumar.
Hello, sir. I'm audible?
Yes, you are audible.
See, ma'am, in the presentation, ma'am already talked about the confined masonry construction, which is related to earthquake, but they did not mention anything about the footing. And one of the queries like that, suppose we are going for this kind of construction technique. I'm an engineer and I'm using a confined masonry for the construction. So in that case, which kind of foundation I need to be choose, and what are the suggestion, and why? Suppose ma'am says suppose I am going for this kind of foundation. So what are the main reason behind that?
Yeah, thank you for the question. Can you hear me? I heard the question. I heard your question very well, actually. Okay, that is a very good question. I didn't discuss foundation. You have a discussion on foundations in the IITGN publication, so you can see how foundations were done there, and also in this NICE publication. So in any case, the answer is the foundations for confined masonry buildings are wall foundations, because the confined masonry is a wall structure. The main question could be, and I don't have, unfortunately, here in this presentation a slide that illustrates that, but as I'm saying, in those two publications you can find. The question is, where do you stop or where do you start reinforcement in tie columns? One solution, so definitely you have masonry foundation, so you don't need reinforced concrete foundation, and you don't need the column footing. So you need continuous wall foundation for sure. That is 100%. The question is, where do you continue? Where do you start reinforcement in tie columns? Because that reinforcement has to start from the foundation. One solution is that the reinforcement is anchored into plinth band. And the other solution that it extends to the bottom of the foundation, of the wall foundation, which means that you need to have a pocket which would be made of reinforced concrete, obviously, let's say if you have a masonry foundation otherwise, or maybe you have the entire concrete foundation, but maybe it's not practical or economically feasible, in which case you would have a masonry foundation, but that part of foundation would need to be in concrete. But it is not certainly a classical column footing, because that is not required. In IIT Gandhinagar, foundation was fully in masonry, and as I said, it is illustrated in that publication, which is free of charge, so you can see the section of the wall. and the reinforcement in tie column was anchored into the plinth band, which was made deeper than usual. So the depth or height of plinth band was, I don't recall, maybe 350 millimeters or more, so that the reinforcement would be properly anchored into that. So there are two options. In any case, foundations are wall foundations or strip foundations. Does it answer your question?
Yes, ma'am. Thank you, ma'am.
You're welcome.
Shall I ask?
Yes, Sunil Kumar, please.
It was a really good session, and I want to know about the madam that is there any chances of the short column effect if we are going to provide the horizontal bands like a plinth band and RCC bands, which is at lintel level, and is there any effect of that on the short column effect or something that, because I heard in one of the session of other STTP and FDP program, and that's why I am asking, ma'am.
Thank you for the question. That is a very important question, because short column effect is really deadly. It's very dangerous, what I would to say, but it definitely happens in columns which are a part of reinforced concrete structure. In confined masonry, you don't have that effect just because you don't have columns. Tie columns, if you are, not you, but let's say I'm color blind, I don't see the difference in colors. You should see that it is all the same color, masonry and concrete, because this is just reinforcement for masonry, which happens to be embedded in concrete. So there is no chance of any of these effects that are characteristic for reinforced concrete frame structures. Any possible deficiencies or weaknesses could be the ones that are characteristic for masonry structures, not for frame structures, because this is indeed a load-bearing masonry structure. That is the assumption, the basic assumption of confined masonry. And I know it is very difficult, particularly in countries like India, where there are so many reinforced concrete frame structures and everybody is educated and trained to design them. But indeed, you should just forget that there is a gray color in these tie columns and tie beams. It is just a part of a reinforcement in masonry.
One more question that shall I ask, ma'am?
Yes, please.
Ma'am, as you said, there is a foundation, is a wall foundation that we are going, and if we have to provide the confinement, then we are going to construct that is a one kind of a floating column. So is it acceptable, because in many reference books that they are informing that you avoid that because the foundation, the column we are taking from the plinth beam or from that level only it is possible. So is there any such kind of effect, or it is acceptable in this particularly confined masonry structures?
No, because you see, you cannot have floating column. Again, floating column is a column in reinforced concrete structure, isn't it? So reinforced concrete frame structure. Again, the tension forces, tensile forces, which are expected to occur, to develop in these tie columns, which are part of confined masonry, cannot be compared in size with any forces that are developed in a column in a concrete structure, because of the difference in the system. In masonry structures, you can see you have so many walls, and these tie columns are just parts of those walls. Whereas in frame structure, you have this grid of frame system, let's say at 5 meters, whatever you use. But so every frame element, every column in that frame structure has a significant loading, even axially, in tension compression, and also combined with the bending moment. So here it's completely different situation, because this reinforcement only takes tension forces. It does not take any bending moments. It is very different system. So it is much smaller. What I want to say is much smaller stresses, and any effects, load effects in these elements cannot be even compared with what you could see in a reinforced concrete frame structure during an earthquake. If you could somehow make two similar buildings, one in confined masonry, one in frame, simply the level of forces and stresses in these elements are really, really different, because masonry structures are very redundant. You have so many walls, and in frame structures you have a much fewer number of those vertical elements, columns, and they have to work hard, and they are subjected to all kinds of effects, like you are mentioning, that is all genuine, but I doubt. And secondly, masonry structures are very heavy, so any, let's say, overturning issues cannot happen in masonry just because there is so much weight in them. So many things it's really different story, masonry and concrete, even confined masonry and reinforced concrete frames can't be compared easily. Just visually you can compare them because they look alike, unfortunately, but that's it all.
Thank you, ma'am.
You're welcome.